In this video, we'll discuss how operational amplifier can be used as logarithmic amplifier or log amplifier. This is the circuit diagram for the operational amplifier as log amplifier. In the previous video, I have discussed how operational amplifier can be used as differentiator and integrator. In case of differentiator, you have a feedback resistance. Here you have a feedback resistance, but in case of log amplifier, you have a feedback diode. This is a feedback diode, and this is your input resistance, and R1 is your input resistance, and Vi is your input voltage, and Vo is your output voltage, and this is the inverting end of the operational amplifier. Negative end is your inverting end. I have discussed about the inverting end and non-inverting end of the operational amplifier. Positive is the non-inverting end and negative is your inverting end, and G is your virtual ground. I have also discussed about virtual ground in the previous video. You first watch my previous video about these terms, then you watch this video. And here R1 is your input resistance. R1 is your input resistance, and the current from the source or from the input voltage suppose equal to I, and the same current will also flow through this diode. Because of the input impedance of the operational amplifier is very high, so the current passing through this input resistance will be same as the current passing through this diode. I have discussed about this thing in the previous video. And what will prove in log amplifier? In log amplifier, the output voltage is a function of the logarithm of the input voltage. The output voltage, suppose Vo, is equal to a constant into logarithm of the input voltage Vi. We have to prove it. And here I have taken Vi is the input voltage, Vo is the output voltage, and Vf is the feedback voltage across the diode, and R1 is the input resistance. And I have also told you that the input impedance of the operational amplifier is high, so current passing through the input resistance is same as the current passing through the diode. In the previous video, I have also discussed about the diode current. The diode current is given by the equation I equal to Is into exponential E into Vf divided by eta into Kb into T minus 1. I have discussed this expression in previous video about the diode current, where Is is the reverse saturation current, and E is the charge of electron, and Vf is the forward diode voltage, and eta is your emission coefficient, and Kb is the Boltzmann constant, and T is the absolute temperature. You have to remember this formula. You should not deduce this formula in your long question. You should only write the diode current is given by the equation this. And I have also discussed the diode current, which is very large than the reverse saturation current. I is very large than Is. I have discussed in diode current. Watch my video about the diode. Then if I is very greater than Is, then what will happen? This term, that is E Vf divided by eta Kbt, this will be very large than 1. So if this term, that is exponential E Vf divided by eta Kbt, this term is very greater than 1, so you can neglect 1 in comparison to this term. So what will be I? I will be equal to Is into exponential E Vf divided by eta Kbt. Then what will be I divided by Is? I divided by Is will be equal to exponential E Vf divided by eta into Kbt. So you write I divided by Is is equal to exponential E Vf divided by eta Kbt, and if you take logarithm on both the sides, then this will be logarithm of I divided by Is, that is equal to EVF divided by eta kbt, and this is your exponential logarithm. So when you take logarithm of this exponential, only you have this term. Then what will be VF? If you solve this equation, then VF will be equal to this term eta kbt will go to the left hand side and divided by E. So VF will be equal to eta kbt divided by E into a log I divided by Is and to the base E. Since it is exponential logarithm, but we know that the current is equal to the voltage divided by resistance, that is the input voltage divided by the input resistance is equal to the input current. So you can see from this diagram, that is the input current I equal to input voltage divided by the input resistance. Then what will be the output voltage? The output voltage is equal to the feedback voltage across the diode. And here the output voltage is negative, because I have told you, when the operational amplifier is connected, the input voltage is connected or signal is connected to the inverting end, then the output voltage will be negative, because the signal will be get inverted in the output. Okay, that is why the output voltage will be equal to negative. So you can write V output is equal to minus of Vf, or Vf is equal to minus of V output. So here the input current is equal to input voltage divided by input resistance, and output voltage is equal to minus of Vf. So what will be Vf? Here Vf can be written as minus of V output. In place of your feedback voltage, you can write the output voltage minus of the output voltage, and that will be equal to eta kb t divided by E into log I divided by Is. And in I, the input current, you can replace or write input voltage divided by R1. So inside the logarithm you have input voltage divided by Is into R1. So log input voltage divided by Is into R1. So from this equation, you can, if you solve this equation or take negative side to negative sign to the right hand side, then the output voltage will be equal to minus eta kbt divided by E into log Vi divided by Is into R1. So you watch this expression. Here the output voltage is proportional to the logarithm of the input voltage, because all other terms are constant. The input resistance is constant, input current is your Is, that is also equal to the saturation current, that is also equal to constant for the diode. T is also constant, Kb Boltzmann constant, then charge of electron, it is also equal to constant. Then also you have the eta value which is equal to the emission coefficient, that is also equal to constant. So all terms involved in this equation are constant, only variable is the input voltage. So the output voltage in the log amplifier is proportional to the logarithm of the input voltage. So, thus you have proved that this is how the logarithmic amplifier or log amplifier operates, or how the operational amplifier can be act as a logarithm amplifier or log amplifier. So in the examination, question will come like this: what is a logarithmic amplifier or log amplifier, and discuss how operational amplifier can be used as logarithmic amplifier or log amplifier, or with a basic circuit diagram discuss log amplifier how operational amplifier acts as a log amplifier.